Yes, let's begin. So is actually Copernicus. Copernicus is the Earth observation program of the European Union, and it offers information services that draw from satellite Earth observation and non-space data, so in situ observations. The Copernicus services are grouped into 6 main chapters that are shown here on my slide. We have the Copernicus Atmosphere Service, the Marine Service, Land Service, Climate Change Service, Security and Emergency Services. Today we will take a closer look at the Copernicus Climate Change Service, also called the C3S because of the 3 Cs, and the main platform where the Copernicus Climate Change Service provides its data is called the Climate Data Store. So yes, this is the C3S that I mentioned. And the Copernicus Climate Change Service includes informations, so observations of the climate system with the latest science to basically develop quality assured information about the past, current and future climates. And that is for both Europe and worldwide, for global scales. The Copernicus Climate Change Service is mainly operated also by the European Centre for Medium Range Weather Forecast, that is the ECMWF, which operates on behalf of the European Union. And basically the C3S provides key indicators on climate change, such as, for example, carbon dioxide and its impacts in reducing glaciers. And the aim of these indicators is to support European adaptation and mitigation policies in a number of different sectors. So the C3S is aimed to inform, improve and promote these data. So to inform basically policy development to protect citizens from climate-related hazards, such as high impact weather events, then to improve the mitigation and adaptation practices for key human and societal activities, and to promote the development of new services for the benefit of society. The link to the Climate Data Store is shown here, but you can also just type the Climate Data Store into Google and it will show up as the first search result. So what types of data are actually available in the Climate Data Store? As I briefly mentioned, there are the data available in the Climate Data Store are the data on past climate, present and future climate. So the data on past climate is covered by in situ or on-site observations. Then we have another set of observations, which are the satellite observations. And we have the reanalysis. So the reanalysis is the data based on observational data, but improved with the combination of forecast models to best possibly describe the past climates. So we know that observations can have their pros and cons, sometimes specifically with observations that are managed by people, there can be mistakes. Of course, this is the observational databases here are not are managed well, but still we have the reanalysis data, which describes the global history of the atmosphere by using a combination of forecast models and data assimilation systems to basically assimilate the observational data, the model data, and to reanalyze past observations. So when you would like to use the best possible past data, I recommend using the reanalysis data. And then we have the fourth type of data, which are the future projections, the climate projections, which simulate the Earth's climate for the future decades, typically until the end of the 21st century. The climate projections are based on assumed scenarios of the greenhouse gas concentrations, as we briefly mentioned in my first lecture. And we have two main groups of climate projections results. The first come from the global climate models, also known as the general circulation models. And the second group of models are called the regional climate models. An example of this is the Eurocordex regional climate model ensemble, which is provided for the European Union. Just to remember from our first lecture together what the climate scenarios are all about. So as you might remember, the climate scenarios represent plausible future conditions based on best available science. To describe this, 5 shared socioeconomic pathways have been developed. These are called the SSPs, and they explore challenges to adaptation and mitigation. The SSPs, as shown here, are the SSP 126, 245, 585, and so on. And these numbers represent the rates of global warming, of additional forcing added to the atmosphere. So the SSPs basically model how socioeconomic factors might change over the century, such as population, economic growth, education, urbanization, and the rate of technological development. And the SSPs are, as I just mentioned, based on the RCP scenarios, also written here in these two figures, which are called the representative concentration pathways. And the letters of the RCPs specifically describe how different levels of greenhouse gases and other radiative forcings might occur in the future. So four RCP scenarios have been developed, which are shown here. So the RCP 2.6 representing 2.6 additional watts per square meter in the atmosphere at the end of the century. Then the RCP 4.5, 6.0, and 8.5. Of course, the RCP 8.5 represents the most pessimistic or scenario in which we wouldn't minimize at all our greenhouse gases in the course of the next century. And just like I added this table in the scope of my first lecture, I added it here as well so that you can easily see which scenario represents which kind of description, which future conditions in worldwide. So for the RCP 8.5, we have the fossil fuel development, and for the RCP 2.6, we have the development with sustainability. Let's continue with the climate data store. So how is actually data accessible in this platform? We have 3 types of access to the data. The first type represents raw datasets. So the datasets that we, as you would imagine, like a CSV or an Excel table, but here they are provided in a bit different formats. But yes, so raw datasets can be downloaded on our own computers and used in our programs or in our data analysis programs on our own computers. Then we have the applications. The applications provide online visualization of data and are shown here on the right figure. And the applications are really nice to use because we don't have to analyze all the data by ourselves. We can just choose what types of data are interesting for us, see if there's an application for it, and then we can use the applications to visualize the data and also download the figures and so on. So there are the applications as the second group of access. And in the third group, we have the toolbox and the application program interface, also called the API. So the toolbox is basically an online toolbox to analyze the data by using programming code and so on. And then to not do this programming online, but on our own computers, we have the API. The API provides easy access to the CDS databases, but still we can do the programming on our own computers, not online, because the toolbox is always online. So these are the three groups of data access. And here on this slide, I also showed the five sectors by which we can browse the available data sets and applications. So first we can choose the product type that I presented earlier. So the projections or the past observations in reanalysis or satellite observations of the past. Then we have the variable domains. We can either choose atmospheric data. We can also analyze land data of the biosphere, cryosphere, and the hydrology. And we also available in the CDS is the oceanic data. Then we have the spatial coverage. As mentioned, the CDS covers European scale and also the global scale. And we have the temporal coverage of the future, past, and present. Then probably quite interesting for you is also the sector chapter. So here we can choose which sector is mostly connected to some of the data sets. So for example, if we come from agriculture, we can just choose the agriculture here, and we don't need to browse all of the data sets and applications that are available, but we can just sort out all the ones that are important for us. So we mentioned that the data is available for various time periods, but as well, the data can be aggregated differently. So that means that the data can present daily, monthly data, average values for multi-decadal periods, which are called climatologies, and so on. And all of this information, what type of aggregation is included in the data, is also shown in the descriptions of the applications and the data sets that we choose. So here I just copied out some of the examples that might come useful to you for your and for your further research after this training, but I will show these examples online as well. So for example, the CDS applications that are relevant for urban areas are here. A few of them are here. For example, the heatwave days for European countries. We have the urban climate, so the mean urban climate for capitals in Europe. Then we have the urban heat island intensity for past periods. And for example, a few of the examples of that are relevant for coastal regions and the tourism sector are presented here. For example, the mountain tourism indicators for Europe. We have the fire weather indicators, indicators of water level change for European coasts, and so on. So with this slide, I would like to finish my PowerPoint presentation, and we'll continue with the data store. Just a moment. Okay. Can everyone see the Google Chrome that I opened?
Yes, I can see it.
Okay, perfect, cool. So I'll just head on to the main page here. So the link to the Copernicus data store is basically just CDS, the Copernicus data store initials, .climate.copernicus.eu. But as I mentioned, you can access it by just typing climate data store into Google. It's not hidden or something. So we have the main page with
Zala, maybe you can share the link in chat.
Yeah, sure. I added it also in the PowerPoint presentation, but of course I'll share it here. Just a moment. Okay. Yes.
Great, thanks.
Yeah, you're welcome. So yes, this is the climate data store. We have some information here at the bottom, how to access the support portal, what the API, so the application, the interface is about. And then we have the C3S Atlas that maybe I'll mention afterwards at the beginning of this presentation. Maybe just a brief notice, as Brooke and I have seen here while we were preparing for a presentation, the climate data store is expected to have some disruptions. So maybe I hope that everything will work well, but sometimes it might take a while to access some of the data or some of the applications. So here we have in the upper part of the page, we have of course the home page. Then we have the search tab, which directly leads us to all of the available data sets and applications. But we can also just here choose just the data set or applications if we want to browse just the applications and so on. We have the toolbox with its description and all of the information. We have the support page, the live page, which I'm actually not absolutely sure what it's about, probably some live help, and then the climate atlas that I just mentioned. We'll just head on to here to the search page. So this is what it looks like. Here on the left side, we have all of the chapters by which we can browse our data that I've also included in the presentation. So the product types, then we have the variable domains, the spatial coverage, the temporal coverage, the sector, and the provider. We can also browse the data by the provider that provided these data sets, but usually this isn't extremely important because all of it is the same quality. So we can also click here on the applications tab to just browse the applications, and here to just browse the data set. And similarly, if we click on this link here at the top page, it leads us, you can see that the page hasn't changed, it leads us to the same page. So it's very not complicated. All clicks lead us to the same location. So we'll take a look at the applications. You can scroll down here and see all of the applications available. We will take a look at the ERA 5 Explorer in just a moment. But yes, so there are all kinds of data sets available. One is also the birch pollen season onset data and so on. And here under the titles of the applications, we have the additional information by which we can browse this database to get to this to these applications. So as I mentioned, we will take a look at the ERA 5 Explorer. So when we choose an application, it leads us to its page. In the first tab, we have the overview with the information on how this data is provided, by who, what variables are used, so what input meteorological variables are used to provide this application. And then we have the output variables. So the output variables in this sense represent more mean values of the input variables and are easier to use and to understand than to just present all of the input variables in their raw versions. So on the right-hand side, we also have the help links to get help to if you have some problems with the application or something like that. We have the publication date and we have the license tab. So here it says that this data is freely available. Usually for most of the data it is like this, but sometimes you will have some further information included in a PDF or something like that. But basically the basis of the climate data store is that all of this data is freely available. We just have to, if we directly use for example, the figures of the application in our research or in our publications, we just have to cite the source, which is the climate data store. So it's all very open. That is the whole purpose of the of this platform. And then we have related data and related applications, which might come useful to some of you. So then in the second tab, we have the application that we came for, and we have the documentation in the third tab, which provides more detailed information on the data sets and the statistical methods that were used to calculate these mean values from the raw input variables. And we have the source code, so which is very useful. The application source code is completely free and very well shown here, so you can easily copy it to your clipboard, and when downloading raw data sets of ERA 5 data, you can actually run this application at home on your computer when you're offline as well. So this is very public and very interesting. But of course, the applications are here so that we don't have to code ourselves. So what is the ERA 5? The ERA 5 is an example of a reanalysis. It's the last generation of the reanalysis data provided by the ECMWF. So this is the beforehand mentioned the European Center for Medium Range Weather Forecast. And the ERA 5, as written here, describes the global history of the atmosphere for the 40-year period of 1979 to 2020. It combines observational and model data assimilated into reanalysis data. So here we can take a look at the application. We have on the right-hand side, we have the variables which we can present. Right now we have chosen the average temperature, that's the default option. And then we can also choose to present states and provinces or not, and to include country boundaries or not. We can, for example, now choose a city from Central Europe. For example, we'll choose Prague. And then an additional tab opens here on the right-hand side. We chose Prague, and on the right-hand side, we will get monthly, because it's written here that the results will show monthly climatologies. We will get monthly climatologies of average temperature. The results are sometimes generating for a longer time, sometimes they're generated quite quickly. Probably it depends on the amount of people at the platform, but I think it also might be a bit slow now because of the disruption that we mentioned earlier. So this is what the results look like. Here are the geographical coordinates of Prague, and then we have the temporal aggregation and the variable drop-down menu. We can choose overview, and various variables will be shown, but we can also just choose temperature. We just want the temperature results, or precipitation, wind speed and direction are shown as well as frost days and tropical nights. So here is a brief description of the climate in Prague for the 40-year period, based on the 40-year period. But here the description is for the 30-year period of 1981 to 2010. That is because for climatologists, when we do our research, the most recent climatology that describes the mean state of the climates is the 30-year period of 1981 to 2010. We do all our research based on this reference period. It's called the reference period. That's why it's written here. So in these 30 years, Prague had a temperate oceanic climate, and the climatology plot below shows all of shows the climate graph. So this is basically the figure which represents precipitation data on the bottom, and then it's combined with temperature data. On the bottom part of the box plots are the minimum temperatures. On the upper part are shown the maximum temperatures, and this graph shows the monthly values, the mean monthly values for this 30-year period. We see that Prague has gets the most precipitation in the summer part of the year, and so on. We can also choose different cities, of course. Let's just take a look here at, for example, frost days and tropical nights, and see what the application shows afterwards. And of course, we also the initial map that was shown here provides us with some information. Here, the average temperature is shown as it's quite unclearly written here above the legend. So we can see that how the temperature, the mean temperature is distributed across Europe. As one would expect, the Alps with the lowest temperatures in the Central European region, and so on. So here on the right-hand side, the results have generated for the frost days and tropical nights. And these are the typical monthly results for the 30-year period of 1981 to 2010, just like before it was with temperature and precipitation. And here we can see that, of course, Prague gets most frost days in the winter period, up till the beginning of March, and the most summer days occur in summer, as expected. Then there are also the tropical nights. The tropical nights are the nights in which the minimum temperature is always above 20 degrees. So for this past period, we can see that this hasn't occurred often in Prague. And the summer days are days in which the maximum temperature is above 25 degrees Celsius, and frost days are basically just days with temperatures, a minimum temperature below 0 degrees Celsius. So this is an example of climatological data provided by the ERA5 reanalysis. Just like with the reanalysis, we can also take a look at the climate projections data. But maybe just so that you will be that we continue with this together, maybe we'll head on to the search page, and we will choose. We will search for the applications for the application together. I'm not sure if we can choose here on the search page. When we just click on the search page, the fifth result is basically the ERA5 Explorer that we have just used, and we can see here if on the right hand side the climate projections are not shown easily, then we will just type into the search bar. We will choose these drop-down menus. For example, here we want to see how the mean climate in Europe will change in the future. So that's why we choose here the climate projections data, the atmospheric data, the surface atmospheric data, and Europe. And we can see how the search results change from based on our filters that we choose here. Okay, so now we got to the temperature statistics for Europe derived from climate projections, and I lost the applications now. Now I got myself lost. Maybe let's continue with the urban data, and then I'll check where I lost the climate projections of mean climate. So, okay. The next application that I wanted to show you was the heat wave days, was the application that was more relevant for urban areas. So, because urban areas are under greater impact of heat waves and urban heat island effects, the heat wave days are more relevant for them. So we can take a look at the overview of this application here. We see that the input variables that are shown in this application are the heat wave days, described as by three different definitions. The first one is the climatological Eurocodex heat wave days definition. The second one is the Euroheat project, and the third one is the national definitions. Then on the right-hand side, we can see the same help link as we had before, but here under the license, we have the license to use Copernicus products, the link to the PDF, where it's described how you should cite everything and so on. But still the the application is free to use and to distribute, provided that we cite it correctly. So let's get on to the application page. we see here on the left one the map of Europe with the number of heat wave days for the for the year of 1986 on presented on the legend part of the map. And for the example, for the default selection of the example of Italy, the result is already presented here on the right hand side. We see that the definition that is the default definition of the heat wave days is here is the Euroheat project, but we can also choose different definitions. For example, sometimes national definitions are the most appropriate to use. That is in the case of Slovenia, at least. So here we can see the number of heat wave days for Italy, the projections data, the graph of the climate projections for two scenarios, for the relatively realistic scenario of RCP 4.5 with 4.5 watts per square meter of additional radiative forcing included in the atmosphere at the end of the century, and the RCP 8.5, which is the currently pessimistic scenario if we do not balance out our greenhouse gas exhaustions. So the number of heat wave days is projected to increase for Italy, especially the difference is the most visible, especially after 2040, when the level of heat wave days is projected to balance out by the end of the century in the case of the RCP 4.5 scenario, and is projected to increase significantly in the case of the RCP 8.5 scenario. Then we can also here we can also scroll in. We can see that the countries are separated by their NUTS regions. So the NUTS level 3 administrative regions as written here. So we cannot we can choose specific regions, not only the country as a whole. For example, we'll choose Niederösterreich, the region, and here is the result presented for this region, the climate projections. Apart from because the climate projections aren't completely definite, they present various possible outcomes of the future. That's why we always have to take into account the uncertainty, and the middle lines always represent the mean values of the climate projections that are most often referenced to in media as well. But we have to take into account that we always have to include the lower and upper limit data as well. So for example, the projected increase in number of heat waves, the projected number of heat waves in 2083 in Niederösterreich its mean value is 16 days per year, but the lower and upper values are 14.9 and 18.48. So yes, you can the results here. We can also download the plots by clicking onto this camera emoji. Then we can zoom into. We can zoom into specific parts of the graph. So the graphs are interactive and quite nice to use. Then we can use the Plotly interface if some of you has it on their computer. So there are quite a few options on how to additionally analyze these results. Yes, so this is it. This is the example of the climate projections data for Europe. Just a second. And now let's continue with the urban climate for cities in Europe. So because urban climates are a bit different to the climates of other regions, urban climates have their own microclimate statistics. That's why I thought it would be interesting for us to take a look at also these statistics presented in this application, because unfortunately the data for now is only available in this form for the period, for the 10-year period of 2008 to 2017, but I hope that it will be updated quite soon. So we can take a look at what the main variables are that are included into these results, which are the temperature, that's not really it would be easier for you to just take a look at the application. Of course, we have the documentation as before and the source code, how to present the results in this application. And here we have the application by itself. So with these location graphics are represented the main capitals and larger urban areas in Europe. And we can scroll in to zoom in a little bit. And for example, we will choose Budapest as an example of our result. Here we have 3 drop-down menus. The first one is season. We can choose either the summer or the winter season. We can choose different variables: mean temperature, maximum temperature, specific humidity, relative humidity, and surface wind speed. And then we can choose the types of statistics. We can choose the mean values or the minimum values represented by the 10th percentile, or the maximum values represented by the 90th percentile, and so on. We will stay at the mean values. And here on this, I will just click here to the full screen because I think that the figure is quite small and you won't be able to see it. Yes, so here on the graph is shown the mean temperature for 2008. And if we choose to click on the arrows, we just we continue on to the later years, to 2009, 2010, and so on. And it's quite interesting to see how the colors change, how the temperatures change, and so on. How the temperatures change from year to year because the scale is always the same. That might be quite interesting to analyze. And with this white is the river is represented. And on the bottom part, we can see the mean temperature graphs, that how the summer mean temperatures change from year to year. We can see that they are in average, they increased in this 10-year period from 2008 to 2017, but we have some year-to-year variations. So this is the example of Budapest. We can also choose, for example, Ljubljana, and a similar situation is shown here. If we hold the mouse at one of these arrows, we can see what the value of the temperature is for this part of the chart. and we can see the differences, the year-to-year differences by analyzing these figures here. And similar to these results here that are represented with these orange figures are the results that I will present now. Let me just click on this. So by clicking on this button here, full screen, we can either go to full screen or to smaller screen, back to the smaller screen. And then the next that I wanted to show you, I can't move this. You can click on the tab. Okay, so we will now go to the search page again, but we will click on the application so that we don't get caught up somewhere else. We will choose, for example, infrastructure, health, and for example, tourism we will head on to afterwards, and water management for afterwards. And we will see how the results change based on our selections here. And this is what I wanted to show you. We have just taken a look at the urban climate for cities for this 10-year period, but similar to these results, a bit different. A bit of a different application is the urban heat island intensity. We will take a look at this application now. So I don't remember if we mentioned this in our lectures or if Tjasa presented it. The definition of the urban, probably you're all well known with the urban heat island effect, but the brief definition is that the heat island effect represents the difference in temperature of the urban area reference to the rural areas nearby. So the rural areas that don't have that much concrete buildings and so on, and they don't, the temperature doesn't increase as much in these rural areas. They, provided that they are green enough, with green infrastructure, with forests, fields, and so on. So this application represents the heat island intensity for European cities, for larger European cities, for the same 10-year period that we have just shown. Here in the overview, we can see that the input variable is, of course, the temperature, the surface temperature, so at the height of 2 meters, and then we have the heat island effect as the output variable. So by definition, the heat island effect also here is described as the temperature difference with reference to the mean rural temperature. So now the default selection is the selection of Alicante. We can also choose, for example, another city. I don't know, or we can choose Krakow, for example. And then we can choose different seasons. Here on the drop-down menu, the heat island effect is not only a summer season, it's not only specific for summer seasons. It can also, of course, happen in winter, but the effect is slightly smaller because of more evenly distributed temperatures. And then here we can choose the select, which we can select which year interests us the most out of this decade. And on the upper part, so in the first line, we can see the daytime and the nighttime results of the heat island effect for this particular year. And on the bottom line, these figures stay the same no matter what year we choose here on the drop-down menu, because these are the mean results for the 10-year period. For as in the first line, the left figure represents the daytime and the right figure represents the nighttime results. We can see that the heat island effect is more pronounced in the nighttime. In the daytime, all of the in average, the surfaces get more heated than during the nighttime when the urban areas emit more heat to their surroundings. So we can clearly see the boundary where the rural areas begin and the urban areas finish. And still with this blue line and the white part underneath, we can see the river clearly. So these are quite interesting graphs for example, when we want to invest into green infrastructure or something like that. We can see which areas, we can briefly see or get a good description of which areas in the city are more under the influence of the urban heat island effect, and where green infrastructure practices would be appropriate. So let's head back to the search results that we had. I just went back here in my Google Chrome, and I wanted now to show you the infrastructure and water management results. Coastal regions, sorry. Now I wanted for us to take a look at what the indicators of coastal regions are showing. So we will choose the first result here. So the application for the coastal regions, the indicators of water level change for European coasts in the 21st century. I just hope that the application will work, because in the morning something didn't work when I tried it out. So here the results that the application shows are a bit more complicated. They're a bit larger in their size. So we have quite a few variables here. For example, we have the tidal rate. We can simulate what the difference between the high tide and low tide is in various coastal regions. We have the total water level. We have the significant wave height, annual highest high water, annual lowest low water, and so on. So there are quite a few different indicators. But if we take a look at the application, we have here first the drop-down menu of the indicators that we can choose. For example, the tidal range is the default selection, and of course the other ones that I just mentioned. We have the significant wave height and astronomical tides, low and high tide, and so on. Then we have also the spatial aggregation. So that means, as I've mentioned in my presentation of the time aggregation, we also have the apart from the temporal aggregation, we also have the spatial aggregation sometimes. So the spatial aggregation just means for what areas the mean is calculated. We can get the results for marine regions, or we can get the results on a coarser or more finer grid. So, for example, here we have with the red colors all of the marine regions of oceanic marine regions are represented here for Europe. And then we have the projections data on the right-hand side. For now, we haven't chosen anything, so that's why the results haven't changed. We can, for example, go here towards the Venetian Lagoon, and click on the geographic location that interests us, and the results start generating. So yes, so because we have selected here the indicator of tidal range, we can see here on the right hand side the average tidal range for this location, quite near to Venice. I haven't pinpointed it completely. So the box plot results display the median and the interquartile range, so the min and maximum result. And we can see how the tidal range is projected to change in relation to the two RCP scenarios. Maybe more interesting than the tidal range would be the mean sea level. Let's take a look. Yes, it's available here. So mean sea level. So how will the mean sea level change in this location? Yes, this. Okay, now it works. In the morning it didn't work. Great. So and this is the result that you hear so much about in the media as well. So the mean sea level is expected to change in the 21st century worldwide, and for this location in the Adriatic Sea, we can see how the annual mean sea level will increase in relation to the both RCP scenarios and their time periods. So for RCP 8.5 in the approximately in the middle of the century, the mean sea level will increase by 25 centimeters, and at the end of the century, in the case of the RCP 4.5 scenario, the mean sea level is projected to change by for approximately 34 centimeters. So I hope that these results will serve you well. The last part that I wanted to show you are the mountain tourism indicators, but we'll just take a look at it briefly. We continue on with the applications tab here and just choose the sector of tourism on the drop-down menu. And we have, for tourism, we have two relevant applications. The first one is the mountain tourism indicators, and the second one is the fire weather indicators for the 21st century, derived from reanalysis for the past and climate projections for the future. So here on the mountain tourism indicators, there are quite a few possibilities how to present the data, but mostly these indicators are related to the skiing seasons. So when the seasons will start, when they will finish, at which altitudes the snow significant snow amounts will be present in the future, and so on. It's a very good application. Here on the left hand side, we have quite a big selection of drop-down menus. We have the number of the indicators. So if we're interested in the number of days with snow depth above some significant threshold, we have the start of season, so that's the skiing season. End of season, we have annual amount of machine-made snow, because we know that not all we can't rely on making machine-made snow in the future because of the temperature conditions. Machine-made snow will also need low enough temperatures, and apart from that, we have the water availability. So we have to have enough amount of enough of water available for making the snow with machines. So that's here we have the winter precipitation amount and so on. What maybe the start of season date might be interesting. Then we have we can choose the snow management configuration, the time horizon, for example, the middle of the century, which type of scenario we're interested in, the statistical indicator, so the mean, minimum, maximum, what elevation, and so on. And for example, we can take a look at two of the Austrian regions. We'll choose, for example, Klagenfurt-Villach and Oberkärnten. And if we choose two regions together, the results will show for both of them. And we can compare which regions might be more fit to continue the skiing, lift, to continue the management of ski lifts there, or so on. So yes, with that I think that I should continue with Rock. So I think that will be all from me for now. And if anyone has any questions or something, we can settle them now or at the end of the end of our lecture. So thank you for your attention, and that will be all from me.
Thank you, Zala.
Okay, then we'll continue in the second part. My name is Rok Puk. I also do some work with Tjaša Pogačar's group, along with Zala at the Biotechnical Faculty of University of Ljubljana. And in my work, I also used Copernicus data. So for example, Zala just showed you the snow indicators. 2 years ago, I think we did a study for where we analyzed the climate impacts, climate projections for Slovenian tourist destinations, and we looked at ski resorts and how the amount of snow at a few select Slovenian ski resorts will change in the future based on a few scenarios. And we use Copernicus data. So we use the data set that underlies the application Zala just showed you. And so now we'll take a look at how we can download this data and work with it further. So as Zala said, there are three main ways to access data from Copernicus. One are the applications, which, as you saw, are relatively simple to use, but are limited, so they cannot display all of the data. And the CDS datasets contain all of the data that can be used and can also be downloaded. But before we take a look at the datasets, I would like to show you the Climate Atlas. You can access the Climate Atlas app from the homepage of CDS up here or down here. And this application is similar to the ones we've seen, but contains a lot of data at the country level and also globally. So here we can select, let's say, European countries, and we can zoom in on Europe by scrolling or using this plus icon. So now we're seeing the mean temperature, as shown here, for a global warming level of 2 degrees Celsius. So here we can set, for example, what would be the mean temperature. So that would be the mean yearly temperature in a world where the global mean temperature is 4 degrees. So we can adjust the degrees of warming and see what the results would be. So now we're looking at mean annual temperature. We could, for example, look at mean summer temperature and how it's distributed. We could also look at scenarios. So we choose climatology and changes. We have the three 30-year periods that Zala also mentioned before, and we can choose a specific scenario. So let's say if we want to see this is the pessimistic scenario, 8.5, we could look at the most realistic scenario, 4.5, and in the long term, so that would be the period from 2070 to 2100. We can take a look at what would be the change in summer temperature. So we should see the mean summer temperature in Slovenia. If we select Slovenia and then click regional information, we also get a graph of the temperature. Okay. So there are also other variables that you can see here. For example, if we wanted to look at precipitation, you can click this raindrop. And let's, for example, take a look at maximum of 5-day precipitation. So these are really big storms that can cause flooding. So let's select this variable, and I'll close this window for Slovenia so we can see what happens globally. So now I have long-term and 4.5 scenario. So let's say the 8.5 scenario. And you can also look at change. So this is what we're seeing now. So for example, for Slovenia, it's a bit yellowish. So if that's correct. So there shouldn't be a big change in the summer precipitation. But we can, for example, take a look at winter extreme precipitation. So we can see that it's a bit green. So in winter, the maximum 5-day precipitation will increase. You can also click climatology here to see the actual values. They're measured in millimeters per day. And we could then compare different time periods. So you could look also at historical periods. As Zala said, we always look at 30-year averages because this period is long enough that the natural variability of the climate approximately averages out. So we might have a year where we have high temperatures and then a year with low temperatures. We usually look at least a 30-year period average. And so on. You could look at additional variables, but we're not going to go into this now. I just wanted to show you that this application is also available. Now, the main way we'll access the data is through the CDS. So we can click data sets up here. And let's take a look at the data underlying an application that Zala showed before for the amount of heat wave days. So if I search for heat wave days, I can find this data set. So this is under data sets, not under applications. Heatwave days and cold spells in Europe derived from climate projections. Now, if I click here, we get a similar page as before. We have a description of the data set. And just like in the app, we have 3 different definitions of heat waves that are described here. And this data set contains the number of heatwave days and number of cold spell days in a year using the specific definition. And as before, we have the license for the data linked here. Most licenses for these data sets are very permissive. We can generally use them for, we can modify them, we can publish them. generally anything we want. Now, our each dataset also includes the documentation, which specifies more precisely how the values were calculated. This documentation is often very technical, but it includes often includes some relevant information for how to interpret the data. Now, under the Download Data tab, we can select the data that we want and download it. So let's select heatwave days, and we have to select the definition. So there are generally no consistent definitions of what a heat wave is. Each country usually has their own definition set by their meteorological office, but for the purposes of this data set, they came up with their own definition of what a heat wave is, and this is the climatological related definition. If you wanted to see exactly how this is defined, we could look in the documentation. And here we have the documentation for this exact data set. And it says that climatological definition is that a heat wave is considered as a period of at least 3 consecutive days on which the daily maximal temperature exceeds the 99th percentile of daily maximal temperatures from May and September in this period of 30 years. So this is the definition that was used here. Just a second. And now let's go back and select which data we want to download. So we'll use the climatological definition. We can also select the scenario for which the projections were made. Now let's select RCP 4.5. And we also can select the format in which we want to download the data. Usually we'll just use a zip file. Now here, these options depend on the data set. Each data set has their own options. This data set has an ensemble statistic option. So when we make climate projections, we usually don't just use one climate model. So a climate model simulates the processes on Earth that impact the climate. And there are many climate models, about 50 models that are used. And these models are developed by different teams and are slightly different. Each team does what they think is currently best. They also improve over time. And some models might have some biases. So one model might underestimate the temperature in one location, and another model might overestimate it. So to get a more accurate picture of what will happen in the future, usually many models are used. So for example, 10 or 20 models are used, and then we look at their mean value that they project, for example, for temperature. And this is the choice that we have here. So ensemble members average means that we take a look at the average that many models have produced. Now, we are also interested in how reliable the projections of climate models are. So as one measure of uncertainty, we can use the differences between different climate models. So this would be this second option, ensemble member standard deviation. This is just some statistical measure of how much different models differ. So if all of the models that were used show approximately the same value, we can be relatively well certain that this is a quality projection. And so the standard deviation is a measure of how much different models differ. But for now, we'll just take a look at the average. So what is the projected value for heat wave days based on the climatological definition for the scenario RCP 4.5. So this is the realistic scenario. Now these fields also have a description. If you mouse over the question mark, they're usually described, but each option is usually also more in detail described in the documentation. Now I can click, usually there's a button here to download the data. Now it says that I have to log in or register to submit a request. So to download data, you need to be registered on CDS. For now, I'll just log in with my account, and then later I'll show you which software you can use to visualize the data and how to register. For now, I'll just quickly show how to visualize the data, and we'll be able to follow along later with another data set. Okay, so now that I've logged in, I have a submit form button here. And if I click it, I'm redirected to this page. So this page, I'll just clear this and do this again. This page shows all the requests we've made. So there is a lot of data on CDS, and we have a lot of choices. And for each of our choices, when we make a request, the data needs to be prepared for us. And this can take from a few seconds to a few minutes. So this was pretty quick. It took just a second or even less. We have a file now that's 42 megabytes large, and we can download it by clicking this button. Okay, so now this data is downloaded, and I can open the zip file. Okay, so now that I've extracted the zip file, I get this file, HWD EU climate RCP 4.5 mean version 1.nc. So on CDS, the data is provided in net CDF files. This is a file format that's a standard in meteorology and climatology. And we can open this file with a few different software packages. We'll use Panoply, which is a software made by NASA to simply visualize this data. So I can just double click this file, and it opens up in Panoply. So this is Panoply, and here we see this data set. So this is the file that I've opened, and here Panoply shows what kind of variables are included in this file. So you have height, latitude, longitude, quantile, and time. And the variable that we're interested in is this, so heat wave days, EU climate. And I can select this by clicking on this variable, and then I can click create plot at the top left to visualize this data. Now this option window, it asks me what kind of a plot I want to create. We'll just use a longitude latitude plot, so this would be a map. And I'll click create. And here we have our data visualized. So this is for the whole world. The data that we downloaded is only in this data set provided for Europe. I can zoom in on Europe by dragging the right mouse button and selecting this area. It can take a second. So here we have our data. So we have heat wave days for scenario RCP 4.5. And the color shows the number of the days. So the blue is 0.1 heat wave days per year. So this is averaged over a 30-year period, or 1 in dark red, one heat wave day per year. Now, if in the window menu, I can select the plot controls, which usually appears automatically when you can plot. And here we can select the time. So now we're looking at the data for 1986. And from this drop-down menu, I can select different years. We see that we have data for each of these years. So for example, if I take a look at 2014, we can see that everything is red now. So because the number of heatwave days increased, so it's more than 1, but the scale is still set to 1. So we have to adjust the scale. And we can do this by clicking here in the plot controls window, show, and instead we use scale. There we go, and we can set the minimum and maximum range of the colors, or we can just use the fit to data button, and then the maximum value is set for dark red and the minimum value is set for dark blue. Okay, so now we can see that Slovenia and Northern Italy has the most heatwave days. There are also some here in Germany, but otherwise it's around 1.5, let's say. Now I can go back to arrays tab, and we can again change time. So for example, you can take a look at the last time period, which is 2085. So this is the RCP scenario, this is the realistic scenario. And now I said that we're looking at 30-year averages. So this is just the middle year of that period. So if we choose 2085, this is the 30-year time period from 2070 to 2100. And we can see that heatwave days have increased by quite a lot in this scenario. Okay, so now we can also look at the data that's underlying this map. Here we have another tab called Array 1. If I click on this tab, I can get to the actual values. So on the top, we have the longitude, so degrees east, and on the left, we have the latitude, so degrees north. Now there are values in the table are NaN, which means that there is no data at these coordinates. So if you look back at the plot, this would be, for example, over the ocean. The data is not provided there, so that's what NaN means. Let's take a look, for example, what are the values here in Ljubljana. Ljubljana is at, I can just scroll or use this scroll bar. Ljubljana is at 14.5 degrees east. So 14.5 is this column, and it's at 46 degrees north. I just found these coordinates on Wikipedia. So for 46 degrees north and 14.5 degrees east, the number of heatwave days per year in this 30-year period, so from 2070 to 2100, is 9.6. Okay, look at, for example, an earlier period. So let's say that we look at the earliest period. So this would be from 1971 to 2000. And we see that in this historical period, the number of heatwave days per year in this 30-year period was 0.7. So quite a big increase is expected in heatwave days for Ljubljana. Okay, now I can also export the data using Plotly. If I go back to this window, I can right-click on the variable and, for example, export as, choose the option export as labeled text. Then we can get a file that we can work further in, for example, in Excel. But these files can be very large. So now it's warning me that this variable includes 25 million elements. So these files can be quite large and hard to work with, but it's possible to export the data. We can also make animations to see how the values change over time. If I go back to the plot window, under File, I can choose Export Animation. And I could say that use the time variable in the dataset for to represent time. And I could then click OK, and then I will get out a video to see how this variable changes over time. Now, this creation of a video can take a few minutes, so I've done this, I've prepared this in advance. It looks like this. So this is the same plot that we had before. I zoomed in on Central Europe. And let's take a look at the animation. So this is the whole, all of the possible 100 time options that we had, just one after the other. And you can see how the number of heatwave days increases. And the time is written here at the top usually. Okay, so this is the basics of how we can visualize this data. One thing that would probably be useful to you is to choose a point on the map and see how the value at that point changes over time. So let's say we looked at these values for Ljubljana. It would be nice if you could make a plot of this value over time. Unfortunately, Plotly doesn't allow that. To do that, we would have to use some programming language or some other software. More about that later. So now I think you can try to visualize this data on your own. I will send you the links for Panoply, so you can install it on your computer. This is the website for Panoply. You can download it by scrolling down, and there's a button here, download Panoply. When you click this link, you have an option to choose. You'll probably want to choose Panoply for Windows. I'll just download this file. And we get a zip file that includes the Panoply program. So now if I extract the zip file, so I get this folder Panoply Win, and if I open it, there's a panoply.exe, which is this program. Now, unfortunately, Panoply requires Java to be installed on your computer. So Java is a software environment that Panoply is made in, and it needs to be installed for Panoply to work. Now, if you're on your work computers right now, Java is probably not installed, so we have to install it. Hopefully you'll be able to install it. I know that some IT departments limit the ability to install software, but hopefully you'll be able to install it so you can follow along. Otherwise, you can just watch my screen as I show the next few data sets and how to visualize them. So I'll also send you a link now to a website where you can install Java. So this is the website. I've opened it here, and you have to scroll down to Windows, and you have to download the JRE. This is the .msi file. This is the one that's 34 megabytes. So you can download this file now. Wait a bit. Okay, so when you download this file, you can run it, and an installer will open to install Java on your computer. I'll show you how that looks like now. Okay, so this should look something like this. When you run the file, you get this setup program. You click next, and then you'll be presented with few options. Computer's a bit slow. And there we go. So here we have to be careful to make sure that we select all 4 options that we have here. So if I click on this set Java home variable, and I click right on the left of the text, I should get a drop-down menu. And we should select this first option will be installed on local drive. And also for the last option, which is the same, will be installed on the local hard drive. This is necessary so that Panoply will work correctly. So all 4 options here should have this small icon on the left, and then we can click next. And then click install, and we have to give the installer permission now. Hopefully that worked. Yes. So now this installation will take some time. I suggest that while we wait for this to install, that you go to the CDS website and register for your account, so you will be able to download the data. So you can do this by going to CDS, and there should be a login/register option in the top right. If now I'm already logged in, I will log out. So if I click login register, I get this window. You can choose create a new account. And you type in your email, country, and it's not necessary to register like you work in an organization, but if you want, you can. And then you click create new account. And I think you will get a link to your email that you write at the top, where you can confirm your registration. So while you're registering your account and you're waiting for Java to install, I suggest that we take a 5-minute break. So you can do this in enough time and maybe get some coffee. Sorry. Of course, if you have any questions, feel free to ask. Okay, so let's continue. Now we're going to take a look at another data set, and hope you'll be able to follow along on your computer. Now I'll share my screen. Okay, so I'm back at the homepage for CDS, and I will look for a data set called extreme precipitation risk indicators. So we've looked at temperature and heat wave days. Now we'll take a look at extreme precipitation. So I'll just search for extreme precipitation. Okay, so this is the data set that I wanted to find, and you can follow along and download the data with me. So it's precipitation risk indicators for Europe and European cities from 1950 to 2019. And again, we have the description of the data set, the license, the publication date, and which variables are included. So we take a look at maximum 5-day precipitation. So this is the maximum amount of precipitation in 5 consecutive days for the user selected month or year period. So let's go under the download data tab, and I'll clear all my choices from before. Okay, now there was high resolution data on precipitation prepared for a few cities that are down here, and we could take a look at just the data for one city, but let's choose Europe, so you get the data for the whole of Europe. And I said we'll take a look at maximum 5-day precipitation as an example. Now the choices here aren't available anymore, so they are gray. You can only choose between those options that are not grayed out. And we have here a product type option. So there are multiple sources. As Zala mentioned before, ERA 5 is a reanalysis product. So this is historical data analyzed using similar models that are used for weather forecast. And this reanalysis lets us get, for example, the temperature or precipitation at some point in Europe at some time in the past. And I think it covers around 60 or 70 years. So EOBS are the observations that Zala mentioned. They may also contain some mistakes. Generally, ERA 5 is the product to use. Now we can also select if you want monthly data or yearly data. Let's select monthly, and we'll see what we get. So these options are all grayed out because they're not available for these variables or for all of Europe. And then we have to select the year. I'm going to select all. So there is a select all button at the bottom right. I'll select all years, and then the format will be a zip file. So I think we've chosen everything we need to. So Europe, maximum 5-day precipitation, ERA 5, monthly, and all of the years. So now you can click submit form, and because there's a lot of data, oh no, it didn't take long. And now I can click this download button to download the data. Okay. Again, we get a zip file. I'll just extract the zip file. Okay, so I get a folder with a bunch of net CDF files. So if you look at the names of the files, they're quite long, but we get max 5 days precipitation, Europe era 5 monthly, and then for year. So for each year, we got a separate file. Now for the format of the data, so how it's organized and what kind of files we get is different for every data set. For this data set, get one file per each year, which is a bit inconvenient, but that's the way it's provided. So now I can open this file in Plotly. If you launch, sorry, not Plotly, Panoply. If you launch Panoply, there should be a window that opens up asking you to choose a file that you want to open, or you can go into the file menu and choose open, and then select the file that we have downloaded. Okay. So I think this is the correct folder. So let's, for example, take a look at the 2019. So this is the last year that this data set includes the data for. So let's choose 2019 and open this file. And again, we get the description of what's included in the file. We have latitude, longitude, and time. And the variable that we're interested in is this precipitation maximum 5-day amount. And I can click on this variable, so it's in blue, and then create plot at the top left. Again, I'll just leave this default option, longitude, latitude, color, contour plot. And when we click create, we again get a similar map. I can zoom in by dragging the right mouse button to select an area, and then I let go, it zooms in. Okay. So if we want to change the color scale, for example, we can go under the window tab and click plot controls. It should be a plot controls option under window, and we get this window same as before. Now here we again have some options for time. All of them are for 2019. This is just only data for 2019 is included in this file, but we can see that we have one for January, one for February, March, and so on. So we chose the option monthly when we were downloading the data. So we have monthly statistics. So if we choose the first option, 2019 January, this is the maximum 5-day amount in January of 2019. One option that is here is also interpolate. This sort of smooths over the data so it's look nicer, but to actually see what the data is like, I like to turn this off, and you can see that it's a little bit less smooth, and you can see each separate data point. Okay, so let's, for example, zoom in more on Central Europe. And we can take a look at 3 different months. So for example, if you choose November, you can see that there appears to have been a lot of precipitation in 5 days in the northeast of Italy. So this is 250 millimeters. That is a lot of rain. And in fact, in November 2019, Venice had, I think, one of the worst floods on record due to a storm, which also resulted in this much precipitation. Of course, also the sea flooded. Okay, so this was one example, and let's also look at projections. So what we looked at now were historical values, so based on measurements. We can also look at the same data, so maximum 5-day amount of precipitation for the future, again, based on different scenarios. So I'll go back to CDS and click on the Datasets tab and search for climate impact indicators. This is the data set I want, temperature and precipitation climate impact indicators from 1970 to 2100, derived from European climate projections. Okay, so again, we have the description of the data set, and you see which time is included, what's the resolution, temporal of the data, and also the horizontal resolution. So we saw that on for the previous data set, we had discrete pixels. So this here is the same. The data is provided on a grid of 5 by 5 kilometers. This is consequence of climate models. Climate models use some resolution where they calculate the values. So we are limited by this resolution. And this data set includes air projections for air temperature, highest 5-day precipitation amount, longest dry spell in days, the number of dry spells in the specified period, and also precipitation. So let's take a look at this highest 5-day precipitation amount. We can go on the download data tab, and I'll choose the climate impact indicators. For some reason, these variables that are in this data set are separated into 2 categories. We can choose, for example, essential climate variables, and see that the last 3 variables are grayed out. So if you want to use highest 5-day precipitation amount, I have to choose climate impact indicators. And I'll check the highest 5-day precipitation amount. And now also we have here a processing type. So most datasets don't have this option, but this one has. If you choose original, we get the values for the highest 5-day precipitation amount as they were made by the climate model. We also have bias-corrected values. So we should always use bias-corrected values if possible. Bias correction is a process where the results of climate models are improved based on historical data. So for example, some model might consistently underestimate the amount of precipitation at some location, and we can find this out by comparing the results of the model to actual measurements at that location. And there are some statistical methods that can correct this bias, and the corrected values are then called bias corrected. So most of temperature and precipitation data on CDS is bias corrected. In most data sets, there's not even an option like here. And if we use the original values, they would not be completely wrong, just less accurate. So it's, if you can, it's better to use bias corrected values. Another option that we have is a relative change from reference period or absolute values. So if you choose a relative change, we would get in percentages what is the increase in the highest 5-day precipitation amount, or we could just take a look at absolute values. Now we only have one option for time aggregation. We need to get an annual mean. So we will get the highest 5-day precipitation amount in a year. And again, for the horizontal resolution, we only have one option. And now we can look at historical data. We can look at separate RCP scenarios. So this is the lowest emission scenarios. This is the realistic scenario, and 8.5 is the pessimistic scenario. We can also choose a degree scenario. If I check this and go down, you can see that I have an option 1.5 degrees, 2 degrees, or 3 degrees. So this would be the values in a world where the global warming value is 2 degrees or 3 degrees or 1.5 degrees. So this is the increase in global average temperature compared to pre-industrial. But we'll instead just take a look at, let's say, for a scenario RCP 4.5. And now we also must select a climate model. So as I said before, usually we look at mean values of a few different climate models. Here we have to select one. For our purposes now, it doesn't really matter, so let's just select the first one. And we also have to use a global climate model. We have only one option. So I selected the CLM and the EC Earth models. And as I said, multiple models are used. This is called an ensemble, and we'll take a look at just one of the models. This is what it's called here, or we only have this option, so I'll just select this. And then we also have to choose the time periods. Again, we have the data averaged over 30-year periods, and I'll select all of them, so we'll be able to compare. So now we have the highest 5-day precipitation amount for this 30-year period, and we'll take a look at annual mean. So what is the projected annual mean of highest 5-day precipitation amount in this 30-year period? Okay, I'll choose a zip file, and now I can submit my request. This is probably going to take a bit longer because there's more data, okay? And I can click download, and again get a zip file. Okay, I'll extract the zip file. And inside the folder, we have 3 files. And it appears that each file is for a different time period. So the first file is from 2011 to 2040, from 2041 to 2070, and from 2071 to 2100. So let's, for example, look at this last time period. I can again open the file in Panoply. I go under File and Open. And again, I have to find the file. I have way too many files downloaded, so I'll just double click on the file and it should open. Yes. Okay, so now we have this data set opened in Panoply. Again, we choose the maximum 5-day precipitation variable and create the plot. There's quite a lot of data, so it might take some time. Okay. And there we go. Now here we have only one time option available. So we have, this is the data for the whole 30-year period from 2071 to 2100. And we have the mean annual maximum 5-day precipitation. And you can see that there are some variations. Perhaps we can set the scale so we get better able to see the differences. We can go under scale. So under in the plot controls window, under show, instead of arrays, we choose scale. And then we can set the maximum value to, let's say, 2000. press enter, maybe even a bit less, let's say 500. So this way we can better see the variations. And we can see that this specific climate model projects quite a lot of maximum 5-day precipitation at a few spots. Now, I think the horizontal resolution was written as 5 by 5 kilometers. And if we zoom in on one area, and again, I'll turn the interpolation off. This is under arrays. There we go. So we can see that here the values vary quite a lot in space. So for example, if you look at the west of Slovenia, also here it's a bit difficult to orient yourself. Here we have the coast of the Adriatic Sea, but it would be nice if we had country borders, and we can also display the borders of countries if we go under the overlays. So instead of arrays, we choose overlays. And then we have overlay 1. Now it says it's earth.cno. We can choose coast countries 1. And if I do this, I also get the outlines of country borders. So it's a bit easier to orient ourselves. So here we see that the projected values vary quite a lot. So for example, at this spot in northwestern Slovenia, it's more than 500, and maybe just a few 10 kilometers south, it's only 200. So in reality, if you look at historical data, it's true that this area of Slovenia gets a lot of high precipitation events, but we have to be very careful in how we interpret this. So this is just one climate model. We saw there are also different climate models, and if you look at the data for different climate models, we might get slightly different results. So some climate models are better at forecasting or at projecting some variables than others. So for example, the temperature is the most accurate. The number of heat wave days or cold spells is also very accurate. Precipitation is a bit less accurate isn't the right word. Uncertain is the better word. So precipitation projections are a bit more uncertain, and especially extreme events are very uncertain. So climate models are better than just guessing, but it's not extremely accurate. So we can't say, okay, at this point here, we'll have 500, and at this point next to it, we have exactly 403. We can't be that accurate. So we have to be a bit careful at how we interpret such projections. So one way to deal with this is, as I said, to look at many different models or look at means and standard deviations between models. Of course, here we are limited, but while CDS offers us here, we could only download the data for only 4 models and for each model separately. So that's just something to keep in mind, especially for extreme events. We have to be very careful at how we interpret the data. Okay, so now that we mentioned precipitation, let's look at another data set for flooding. I'll go back to the data sets on CDS, and I'll search for flood indicators. And this is the data set I'm interested in, flood risk indicators for European cities from 1989 to 2018. So they've analyzed the historical data for a few European cities. I think there are 20 of them. And we have the variables such as water depth. So for example, if you have a flood, what will be the water depth at a certain location in the city? So what was? This is the analysis of historical data. Now here the events are given using their return periods. So for example, we talk about 1 in a 100-year flood or 1 in a 50-year flood. And this specifies how likely that event of such magnitude is to occur. So for example, 1 in a 100-year flood, if we would expect to happen only 1 in a 100 years. Of course, it can happen more often. I think in Slovenia, we had 1 in a 100-year precipitation event last year, and also 1 in a 100-year precipitation event 2 years ago. So this is more meant as a long-term average. So for example, if something is a 1 in a 5-year event, and let's say 200 millimeters of precipitation is 1 in a 5-year event. This would mean that they arrive at this value by looking at historical data. So for example, for the last 60 years, and look at how probable it is that such an event occurs in that time period. Now, we generally don't have 200-year or 500-year years of data, but we can still say 1 in a 200-year data would look, 1 in a 200-year flood would look like this, because we can use some statistical models that let us estimate events for what would be the magnitude for even some rare events, even if you don't have such a long period of historical data. But of course, these are more uncertain. So we know very well what a 1 in 5-year flood looks like, because we have a lot of historical data. So this data set contains water depth for a given flood. So 1 in 5, 1 in 10, 1 in 25, 1 in 50, or 1 in 100 years. We also have some data on the expected damage in euros per square meter. They used some estimates to estimate what the cost of the damage was. So let's take a look. We'll look at water depth. And let's just say, I'll just clear our options. We'll take a look at 1 in 50-year flood. And let's say we look at Vienna. Here we have an elevation model. We only have one option, which was the first one, and a zip file. Okay, and now I can submit my form. Here we go, and I can download the data. And again, I open the .NET-CDF file in PowerView. Okay, so now again, I have all the variables in the file. We're interested in water depth. So then it's not responding. I'll close it and open it again. Okay, so we have our water depth data set. I'll select the water depth variable and create a plot again, longitude, latitude. It will take a bit longer because there is very high resolution data for cities. For before we had data points on a grid of 5 by 5 kilometers. Now I think it's just it has a resolution of a few hundred meters, so there's a lot of data. Perhaps while we wait, I can show you what are also the other ways of accessing data. So now we took a look at Panoply. This lets us easily visualize a map. But for example, we might want to look at just one point and see how the value changes over time. So this is, for example, on the project that I worked on, we looked at projections of snow precipitation at the point of ski resorts. So we chose a few ski resorts in Slovenia, and we wanted the data for that exact point where the ski resort is. And we had the projections for the amount of snow for 100 years, and we wanted to see how it will change over time. So for example, what will be in one 30-year period, the amount of yearly snow precipitation, and then another 30 year and 30 years later. So to do that, the easiest way is to use some programming language such as Python or R. And this in Python or R, we can do whatever we want with the data. Here in Panoply or with CDS applications, we're very limited in what we can display and analyze, but in these programming languages, we can do whatever we want. But of course, this requires some basic knowledge of programming, so we won't cover this in depth. Here I've gathered a few links where you can find examples of how to do this in Python or in R. Okay, now the data can also be displayed in other applications made for analyzing geographical data, such as ArcGIS and QGIS. There you can also display the data and maybe some additional map overlays. So for example, if you wanted to say have a map of the city and have the values displayed on top of the map of the city with some colors, that will be possible in, for example, QGIS. I think it's also possible to get the time data for one specific point in QGIS, but I'm not very familiar with it. Okay, so let's see if we got our map. Yes, we did. So here we have our water depth for Vienna. Now, of course, we have to find Vienna now. Again, it takes a while. Okay. Here it is. Now, what I mentioned before would be useful now if we had a map of the city and these values overlaid on top. Unfortunately, this is not possible in Panoply. So here we have our data. This line here is the Donau River, and this is the coast of the river. And you can see that this is a 1 in 50 years flooding event. And you can see that a lot of this coast near the river here was flooded, and also many specific spots in the city. So if we have a map like this, it's hard to orient ourselves. So maybe it's easier if we plot the grid of coordinates. So if we go on, instead of arrays, I go under grid. Currently, the grid that was displayed is separated by 15 by 15 degrees. I can set it, for example, for 0.1 degrees And then you get a few more lines on the screen, which represent the coordinates. Of course, I can always look at the table of data here. And for example, see the color here represents the depth. So here it seems like there was a very deep water area in this. No, so this is the average for a 1 in 50 years event. Okay. So one last data set that we'll take a look at is actually not on CDS, but on ADS, which is the Copernicus Atmosphere Data Service. So let's take a look here. So Copernicus Atmosphere also provides some forecasts for the air quality, which might be of interest to you. I'll send you a link to this website now. Okay. So right now, the atmosphere data and the climate data is separate, but as Zala said, this whole platform is currently being renovated, so there might be some disruptions, but in a few months, all of the data sets should be on one platform and probably more easily available, but we don't know much how that will look like. So here we have this data set for European air quality forecasts. This is updated every day. And we have a lot of variables. So we have like for forecasts, for example, how much dust there will be in the air, how much PM10 particles, or pollen and sulfur dioxide, and so on. So let's take a look, for example, at the dust. We had a big amount of dust in the air, I think a few weeks ago, maybe a month or two. And that was very well forecasted a few days in advance by this system. So let's choose the dust. And again, here for weather forecast, they also use an ensemble of models. And we'll just take a look at the ensemble median, not one specific model. And we can also choose the height meters above the surface. Let's just say at ground level, so 0. And we have to choose the range of our forecast. So let's go to this year. So 2024, we're in April now. And let's choose today's day as start. And I think we also have to choose, yes. So we'll choose the today's forecast. So we have the same start and end date, and this will be the forecast. This is produced today, probably around midnight. We choose the forecasts and the time. So when the forecast was produced, we only have the midnight option, and now we choose the lead time hour. So this is the time in the future that the forecast is made for. So for example, 0 would be the at midnight, what is the forecast for the dust concentration over Europe. Then you can also look at 24 hours or 48 hours in advance. So that will be what will be tomorrow's concentration of dust, and what will be that in 2 days. And let's also choose, for example, 96 and maybe also 72. So 1, 2, 3, and 4 days in advance. And we can also choose the area for which we want the forecast. So I'll just choose a smaller area than what's drawn here. So there will be less data. Let's choose, for example, Southern Europe, because dust usually comes from the Sahara. Okay, so you can just use this pencil to draw the area that you want to get the data from. And I'll choose the net CDF data format. This is what you can open in Panoply. There's also a GRIB format, which can also be opened in Panoply, but it's less common. Okay, so now I'll submit the form. This will probably take a while. Okay. And I'll download the data. And again, open it in Panoply. So we have our dust variable here. I'll select the dust variable and create a map. Okay, so now we have the area that we selected. I'll zoom in. Okay, so this is the dust concentration in air in micrograms per cubic meter. We see that today at midnight, there's apparently a lot of dust in this area in Northern Africa and not much dust over Europe. And we can also choose one of the 5 times that we chose when we downloaded data. So we chose the 0, 24 hours in advance, 48 hours in advance, 71, 96. So let's, for example, look at what will be the concentration of dust tomorrow. Okay, so there will be a storm here. Okay. So not much interesting will happen over Europe, perhaps only the next 2 or 3 days, there will be a bit more dust over Greece and Turkey. Usually when there's a big dust storm, such as a month or 2 ago, the whole area over here over Southern Europe would be in this red color, so very high concentrations of dust. So this data set is updated every day at midnight, and it can be used for this data, again, can be used according to this license in other products that can also be published. Now we've looked at how to download and display data, but in some systems you might want to access data automatically. So it's possible to do this, for example, in Python, and CDS provides a climate data store API that Zala mentioned, and this lets you automatically access any data using code. Here's an example that was just taken from the CDS website. I have a link here for a tutorial on how this can be done in Python. So we just select the data set and the variable, and for example, here for the ERA 5 reanalysis, the year, month, day, time, and format, and then the data is downloaded. And this could, for example, then be opened using one of these packages in Python or R, and then included in your systems. So I think this is all from me. If we have any questions, they're welcome.